All right, class, I'm trying this makeshift other way of filming the video, so hopefully you guys can see it better. I was told by a few students if I can go back over graphing functions and making sign diagrams for first and second derivative as we did in class in that section 2.2. I realized many of you had missed that class. And then I started the videos after that section. So here is one more example for you. So it says to make a sign diagram for the first derivative showing all critical numbers and intervals of increase and decrease. So here's our function. All right. So that's what I'm going to do first. So sure enough, we have to find the first derivative. Yes. And that would be 3x squared minus 6x and minus 9, right? Okay. Now, what do we want to do to find the critical numbers? We want to set that derivative equal to 0 and solve. So sure enough, I'm going to factor out a 3 here. And then I can further factor out this trinomial here into an x and an x. Numbers to multiply to -3 and add up to -2, or -3 and +1. So the two solutions to this would be 3 and -1. So as we had said, these are critical numbers, okay? So you find critical numbers where the derivative equals to 0 or it's undefined. Now, the undefined again won't be the case for this function. You get undefined when you divide by 0, so if there's no division, there's no way this is going to become undefined. Good. So let's make a sign diagram now for this. So here it is. We'll put the x's on top, and that goes from -infinity to +infinity. And it's important to place those numbers in order from smallest to largest value. Then here is the derivative. And then based on what happens to the derivative, we will draw conclusions about the function itself. Okay. All right, so we know that the first derivative is equal to 0 at these two values. That's how we found them. Okay, I need a sign. So it's a sign diagram. So is it positive or is it negative? Yes? Okay, there's the sign diagram. All right. So all you have to do, I said, is pick a test point in between these values. So if I pick, let's say, a 0, which is in between -1 and 3, and plug it into the first derivative, you see that you get a negative. Yes? Okay. Then you can plug in a 4 if you want. And if you plug it in, I'm going to tell you, you get a positive value. And the same thing, this side here is going to be a positive. Good. So what does that mean for the function itself? Well, where the first derivative is positive, your function's increasing. So where does it increase from? It increases from -infinity to -1. Where the derivative is 0, the function evens out. Yes, it comes to a horizontal tangent line. Yes, the derivative is 0 means that the tangent line is horizontal. Then negative derivative means the function's decreasing, evens out again. And then positive means the function's increasing. So here it is. You're going to have a maximum here when x is -1. You're going to have a minimum here where x is 3. I will also make that clear on the graph. Okay, so that's our sign diagram for the first derivative. Now, let's take the second derivative. So, okay, what's the second derivative? Well, that's going to be, looking up above, that's going to be a 6x minus 6. Yes, I still have that in my picture. Good. So what do I want to do with the second derivative? I want to set it equal to 0. And then the solution to this being a linear equation is easily going to be that x is equal to 1. So we're going to use this point here to make a sign diagram for the second derivative. So here it is. I'll put the x's, the second derivative, and then I'll draw conclusions about my function from this second derivative sign diagram. So what is the only number that's of importance here? The 1 that we found. And sure enough, again, the number line stretches from -infinity to +infinity. And in between there, there's the 1 that somehow is going to make a difference. Now, what happens to the second derivative at 1? Well, it's 0. Yes, that's how we found it. Plug in a 1 in here, you'll get a 0 for the second derivative. Pick a value in between negative infinity and 1. Let's say 0 is in between these two numbers. Plug in a 0 here, and what are you going to get? A negative 6, so it's a negative value. Plug in a number more than 1, let's say a 2. 12 minus 6 is a positive value. So what does that mean for the function itself? Well, where the second derivative is negative, you get a sad face. It's a second derivative, right? So we're talking about concavity intervals. Okay, where the second derivative is positive, you get a happy face, right? So the graph is going to be concave up. So it's concave down from negative infinity up to 1, and it's concave up between 1 and infinity, yes? And because we're changing concavity where x is equal to 1, we are going to get an inflection point here, okay? All right, so here it is. We have the sign diagram for the first derivative, we have a sign diagram for the second derivative, and really even if you look at this sign diagram, these two diagrams are very consistent to each other. Why? Because you see the graph is looking down, and then somewhere in between here, what do I mean in between here? In between negative 1 and 3, the graph starts looking up. And now we know that that value where the graph starts looking from looking down to looking up is 1. Okay, so what I'm going to do next is put all this to good use to graph the function. So to graph the function, we definitely need a table of values. And where do we plug in those numbers? Really importantly, in the function itself. Yes, this is what we're graphing. So here I have it. I'm not going to put negative infinity to infinity. What I'm going to put in are the values that we found up above, right? Which are negative 1 and 3, because these were my critical numbers, yes? Negative 1 and 3 we graph from here, and the 1 value that we grab from the second derivative, important point. So all I have to do is plug into the function itself. So I'm going to write the function itself again because we passed it a while back. So the function itself was x cubed minus 3x squared minus 9x plus 2. Okay, so if I plug in a negative 1, I'm going to get a negative 1 minus 3 plus 9 plus 2. That's about 11 minus 4, that's a 7. Plug in a 3, and that's 3 cubed, which is 27, minus 3 times 9, which is 27, minus 9 times 3, which is 27, plus 2. So the answer is going to be a negative 25. And then finally plug in a 1. So when you plug in a 1, 1 cubed is 1, minus 3 times 1 is 3, minus 9 times 1 is minus 9, plus 2. So we get a negative 12 plus 3, which is a negative 9. All right, so these are the points I'm going to use in order to graph this function. Okay, so I'm placing them on the xy plane. And here it is. So I have the point of coordinates negative 1 and 7. And here I'm going to go by 5s. So 7's about here. And then I have the point of coordinates positive 3 and negative 25s, which is why I went by 5s. I'm still trying to keep it to scale. And then I have the point of coordinates 1, negative 9, which should be about here. Okay, so based on this, the graph is still first going to go up until it reaches an x of negative 1. Then it's going to start looking down, and what happens when x is 1? That's when your concavity started changes. So from here on out, the graph is going to have to start turning and looking up. And it goes down where x is 3. and then it's gonna go back up. Okay, so again, how did I know that? Out of my sign diagrams, yes? It says right here, at 1 is where we're changing concavities, right? So the graph starts looking down up until x is 1, right? So it's about the x values. And then it's going to start looking up after that. What else have we found from here? That at -1 we have a maximum, and at 3 we have a minimum value, right? It's going to go up until it reaches this x of -1. So it's going to go up until it reaches this x of -1. Then it's going to go down until it reaches this x of 3. And then it's starting to look back up. So here on the graph, I'm going to say this is my inflection point. This is my local min. And this is my local max. And I'm done with this problem. Beautifully done.